All right, so just a reminder, next Thursday will be exam 1. It's take home. You'll have the day to do it. If you have issues with work and you don't think you have enough time Thursday to do it, send me an email. If enough of you email it, we'll adjust it for everybody. If just 1 or 2 of you need some special, not special, but if you need a schedule adjustment, I'd be happy to do it. So reach out to me, let me know. I know a few of you typed into the chat last week or last class that you might want to do that. You got to let me know, and we'll help you out best we can, and then everybody wins. Okay, so all right. So I posted a homework. So let's sort of regroup where we're at before we talk about those problems, because my feeling is there will be questions, because there always is. So last class, our last topic was what's called continuity. And this is a property that a function can possess at a particular value or on a particular interval. So I can't stress enough that this is a very important concept. And so our calculus definition for what does it mean to be continuous, this means the following. So continuous at a point A, it means this very loaded yet concise statement. So my advice for those of you who really want to learn this stuff is to think about what that little limit statement says. Continuity is not just saying that the limit exists at a point. It's saying it has to be a very specific value. It has to be the output of the function at that given point. So let's reiterate what this means again. This, I'm going to put it in a box because it's important. This little purple creature means really 3 things. So let's emphasize what it means. So this statement, the limit as x goes to a of f of x equals f of a, really means 3 things, all in one. The first and most important thing, which wasn't true, this wasn't necessary for a limit in general. So when we define limits, we didn't, a function can have a limit at the value a even though f of a doesn't exist. We saw plenty of examples of that. But what this sentence up here means, by us actually writing f of a in the statement, what we're saying most importantly is that f of a is defined. The second thing we're saying is that the limit does indeed exist. So that means the left and the right-hand limits at a must both be the same number. And then last but not least, what it's saying is exactly what it means, that the two things are indeed equal. So there are going to be lots of limits that we've computed already and that we will compute in the future, where the limit exists even though the function's not defined at a given point. That is not going to be the case with continuous functions. And so what does this mean in sort of layman's terms? So in English, this all means the graph of y equals f of x has no holes or jumps. That's what it means. So we can sketch it, we can graph it without ever picking up our pencil. Okay, so we told you last class that essentially all the functions that you are familiar with are continuous on their domains. And so we asked you to sort of, at least, I keep saying we, I guess it's me that's asking this. On the homework assignment, we're giving you some questions that are sort of, I don't want to say it's testing, but assessing that you understand these ideas. So I think it'd be a good idea for us to look at that, some similar examples. And then I hope if you have questions, you guys will ask particular questions. That's the idea. Lord knows if you'll actually do it, but I can dream. Okay, so let's pull it up. The most recent homework was homework 4. And so what I did is I asked you some questions, and we're going to do some similar examples. Does anybody have a question? Comment, concern? Okay. So let's do some examples to help you with homework 4. So when you do the homework, I would encourage that you look at these things. So let's look at a problem. Let's call this 1. So I could ask you something like, is f of x equals 5x cubed minus 6x squared plus 10 continuous? And the answer is yes. Now, why though? So one of the problem solving habits I want you to get into in this class, and for those of you who will take more math, is you don't just want to say something is yes or no, or something is this property or that property. What you need to do is you need to provide evidence to support this. And so when I say that something's continuous, why is it continuous? Well, I should tell you, the reader, in fact, what line of reasoning am I using to verify my claim? Well, here it's pretty direct. All polynomials, and that's what f is, are continuous. That is a fact that you should be well versed in. All polynomials are continuous. Does anybody have a question or a comment? Okay, so that is all the evidence or all the supporting evidence we need to give to tell the reader that this thing's continuous. Okay, so what if we look at something slightly different, like is, let's say, g of x equal to 1 over x minus 2 continuous. So the answer here is also yes with a but. So it's continuous at all inputs except one number. So it's continuous at all x except the value 2. So g is an example of what we call a rational function, and rational functions are continuous at each point they are defined. Does anybody have a question or a comment? So we can write this answer a little differently. This is what some books like to do. So if we go to the next page, some people might write this in set notation. So we may write that g of x equals 1 over x minus 2 is continuous on negative infinity to 2, 2 comma to infinity. So some of you may have seen this symbol before. This is a U. This is called the union symbol. You can think of it as meaning that x is in one or the other. So you can think of it as a symbol to represent the English words and or. Does anybody have a question about this? All right, let's look at another example. So let's ask, where is this guy? So let's say negative x squared and x plus 2. So we're going to have a piecewise function. And this function is going to be defined like this. When x is less than or equal to 1, we use the rule negative x squared. And when x is greater than 1, we use the bottom rule. So we want to know, where is this guy continuous? So let's think about how we might answer this question. Each piece is a polynomial, so we know each piece is continuous. The problem is, do they match up at the point 1? So that's what you have to analyze. So let's think about what we can say about this guy. So if we go to the next page, so you need to note each piece is a polynomial and hence continuous on the respective domain. Now, the only issue is at x equals 1. Is the limit as we approach from the left of 1 of f of x equal to the limit as we approach 1 from the right of f of x? There's not going to be an issue anywhere else because both pieces of my function are continuous. They're both polynomials, so they're continuous. And so the only question we have, and if you tried to graph this, you would notice it, is you say, okay, there is a possibility that there's a jump or a hole at 1. And we need to figure out if there is, and then what does it mean if there is? And then if there's not, what does that mean? So hopefully, if you're confused about what we're trying to say here, you ask. I'll give you a minute to think about what you might want to say, or if maybe you're taking a nap, I don't know. Now, to point out, when I say on the respective domains, what I mean by that is in the given context. I'm only defining negative x squared up to 1. And then I'm only defining the other piece when x is larger than 1. So we can compute these two values and see if they're equal. So note, or well, I guess, if I approach from the left-hand side, that means that x is approaching when it's less than 1. So if I go to my rule, that means I'm using the top. I'm using the negative x squared piece. So this is the limit as x approaches 1 from the left of negative x squared, which of course is negative 1. Now, what if I come from the right? If I come from the right-hand side, I'm using the bottom rule, which is x plus 2, right? Is it x plus 2? Yeah, x plus 2. And when I compute the limit of this, I get 3. Well, clearly, 3 and -1 aren't the same. So before we go to the next page, let me reiterate what our reasoning is here. We have a function that is defined piecewise. Each piece is a polynomial, so each piece is continuous. The question is where the pieces are supposed to come together at 1, we need to know, do they come together? And based on this analysis of a left and a right limit, they don't come together. When I come from the left, I'm down here, and when I come from the right, I'm up here. So the conclusion is that the limit as x approaches 1 of this function does not exist. Hence, f of x is continuous for all x not equal to 1. So in other words, if you want, f of x is continuous on -infinity to 1, union 1 to infinity. We do not include the number 1. It's discontinuous there. Now, by the way, if you sketch the graph, you would verify this. So we can sketch this. It's pretty straightforward. So if you sketch what the graph looks like here, it's going to look like this. You have -x squared here, this parabola, and then from 1 on you have 2 plus x, which looks like this. So that's what the graph looks like if you graph it carefully. So we can plot some points to be real specific. This is -1. Oops. This is the point, for example. Oh, hold on. I lied. I drew that wrong. No one yelled at me. So really, at this point, it looks like this. So the graph looks like that. Does anybody have any questions or comments? So, you know, a lot of times students will say, well, what kind of physical thing in the real world looks like something like that? Well, there's lots of things. I mean, the most basic thing that we can describe that has a jump is a switch, an on or an off switch. Off, on. On, off. So you can imagine that when you hit a light switch in a room and it turns the light on, you can imagine that the function that's describing that current goes from on, off, or excuse me, off, and then jumps up to on. So there's lots of things in the physical world that can be represented by jumps. So discontinuities are everywhere. And so that's why we like to study and analyze them. And we're going to show you one of the more useful applications in a second of what continuity gets us. Does anybody have a question? Okay, so here's an interesting feature of this function that is going to sort of lead us into our next topic. If you notice this, if you look at this graph, you might make the following observation. So the function above, let me phrase it more correctly, is that it never for example, takes on the value of 1. So another way of saying it is that is, there was no x with the property that f of x equals 1. There's no, you can never find a value, plug it into that function, and it's going to spit out 1. It's just never going to happen. And that's an interesting feature. And if you look at this, the same thing you could say for 2. And in fact, any value between 3 and 0. Now, it will take on 0, but it won't take on 3. So let's make a note of that. So it's never going to take on values in 0 or 3. You could spend the rest of your life trying to find a input that's going to spit out, excuse me, I wrote that wrong. Again, must have had a stroke today. It never takes on values in open 0, close 3. So this is a little more conceptually difficult to understand. But if you go back and look at the number 1, for example, or 3, if you look at the definition of the function, there's no way that you're ever going to get either one of these to equal 1, at least with the restriction of the domains here and here. Does anybody have a question? Okay, so cool. No questions, no comments. Okay, so let's sort of transition into our application here. So a common problem in math, science, and when I use the word science, I don't just mean chemistry or biology. I mean engineering, I mean social sciences, economics, finance, whatever. So a common problem in math and science is solving an equation such as f of x equals 0. Well, let's be more general. Let's state it in the most general setting. So we typically, we'll use L here, why not? I mean, you've spent a lot of your life solving basic equations, and that's an example of this. So if you go back to homework one, one of the things that I asked you to do, pull it up just so we can remember it. I'll share it with you. So if you go back to homework one, hopefully you can see my screen. I gave you this problem. I said, use Desmos or any device to estimate the solution to this equation. And then I prompted you with, can you solve it by hand? And as we pointed out, this cannot be solved necessarily by hand, at least in an easy manner. And in fact, most equations that we encounter cannot be solved using algebraic means. So let me make this very clear. So it turns out this is difficult or impossible to always do using basic algebra. And when I say basic algebra, that's the stuff that you learned up through high school, solving equations. So what we need is a better way. And so what we've done is we've developed algorithms. So luckily there are algorithms that computers can use to approximate solutions. Provided one exists. So let me illustrate a problem to you. I have an equation I want to solve. It's an ugly equation. It might have sines or cosines. It might have exponentials or logs. It might be a polynomial of degree 14. I don't know. It can be a really ugly equation. There are algorithms that I can go to a computer and I can run the algorithm, and the computer will approximate the solution to any degree of accuracy I want, provided the solution exists. And so that means, from a theoretical standpoint, we need some assurance that if we're going to go run an algorithm, go run a computer program to help us solve a problem, we need to know that the solution actually is out there for the computer to determine. Because if the computer is looking for something that doesn't exist, it will run forever. So if the function f of x is continuous and L is between f of a and f of b, or f of b is less than L is less than f of a, then at least one solution exists. And what guarantees this is what's called the intermediate value theorem. So let me be a little more careful. So let's assume that f of x is continuous on a closed and bounded interval, a comma b. And let's give the solution a name. And what's important to understand is that C has we can even not only tell you it exists, we can tell you where its values are located. So C must be between A, and it must be, it must be greater than A and less than B. So what does it mean for C to be a solution? Well, it means f of C actually equals L. Does anybody have a comment or a question? So there's a lot of scary stuff right now on this whiteboard, and it doesn't have to be scary, but what I highly encourage you do is you convince yourself that you can learn it, and then go out and learn it. Do not be afraid of all the symbols or the letters as they are. They're not going to hurt you. That said, it takes a little bit of sort of determination to truly understand this. It's on one hand, it's a conceptually difficult idea to verify, but on the other hand, it's also intuitively clear. And we'll show you what we mean by that in a second. We're going to draw a picture. So let's draw a picture. So first off, let's remind you what it's called. So it's called the intermediate value theorem. So it is a theoretical tool, and it's a theme that is very important, particularly in what we call applied mathematics. So things like physics and engineering and economics and things like data science and statistics. Anywhere where we're using math to solve real world problems, there's this theme that pops up. And so let me explain it to you. Many problems are very difficult to solve by a human. For example, there are many equations, whether they are algebraic equations like you're familiar with, or maybe they are large, what we call systems of equations. Maybe I have 100 equations with 100 unknowns and I want to solve it. Or maybe I have these things that are called differential equations that you'll learn about in Calc 2. Suppose I have some complicated equations that I want to solve. Well, what often happens is they can't be solved by hand, so I need to use a computer to help me solve them. The problem is if I go to a computer and I write computer code to solve a problem, how do I know that the computer's answer is accurate? How do I know it's valid? How do I know how accurate it is? And so this is all part of a bigger picture here. And the most important thing we have to get right before we even get to a computer, though, is we have to be able to guarantee that something is going to exist. If I'm going to go ask the computer to look for something and find it for me using some sort of algorithm, I have to have confidence that what I want it to find is actually there. So what the intermediate value theorem does is it guarantees that there are solutions out there. And so once we know they're out there, then the next thing becomes, how do we find them? How do we determine their value? And right now you might be thinking, like, what does he keep talking about? How do we find? Who cares? What do I need? I don't know. If I'm a banker, I might want to think about finding an optimal interest rate. Or if I run a business, I might want to find an optimal price point for my different products that I sell. And it turns out to answer these types of questions and many, many more, we rely on computers to solve complicated equations. And when we rely on the computer to solve complicated things, we best make sure that the solution's out there somewhere. So the intermediate value theorem is this very cool thing because it's what we call in math an existence theorem. It tells us something's out there, it just doesn't tell us what it is. So that's kind of a strange thing, but it's also very intriguing. There's lots of important existence theorems that are useful, and again, it's just one of these things. For you to have an appreciation for it, it's going to take some deep thinking. Okay, so let's draw a picture. And by the way, if you need to say anything, interrupt. I don't mind. If you have a question, hell, you can talk about anything. It doesn't even have to be math. Maybe you're like O'Grady. How do I get my credit rating high? I say, take out a credit card and pay it off every month, and then you have a high credit score. See, you learned something. All right. Let's draw a picture and sort of convince ourselves why this thing makes sense. So let's just pick two values for A and B. Let's say I call this A and I call this B. And let's draw perhaps what some generic function. Can be anything, but we want to make sure it's continuous. So let's draw something like this. So here's our function y equals f of x. And so here's the point. Let's get a different color. Here's the point b comma f of b. Here's the point a comma f of a. And let's suppose, you know, so just so we all know that this height right here is f of a. If I draw, this is f of b. So since that blue curve is continuous, it has to take on every single value L that's between f of a and f of b. So if I were to come over here and sort of look at this point, well, what is this point? Well, it turns out it has to exist, and we said in C, so this is the point, C comma L. And the thing to note is note f of C equals L. So being that that blue curve has no jumps or no holes, we know that that C has to be out there. We just don't know what it is yet. But we'll show you one way of finding it in a little bit. Well, in a couple classes. But there's plenty of algorithms. You might even think of how you might do it. There's a very intuitive way of doing, although it's tedious to do by hand, but there's a very, you know, ingenious way. I remember when I was in algebra class in high school, we had a pretty good teacher, and he said, "Here's what we're going to do," and then gave us a little, like an hour and a half, and we worked in groups and we figured out a systematic way of figuring this out. And if you're interested in what that way is, it's called the bisection method. If you want to Google it, we're not going to talk about it, but you could. It's there if you want to learn about it. Does anybody have a question about this? Okay. So let's look at an example of so let's look at a function. Let's say f of x equals x. Let's say, well, let's be a little more coy. So let's say 3x to the 15th plus 6x cubed plus 5. So is there a solution to f of x equals 1, which is, if you write it out, that's the same thing as 3x to the 15th plus 6x cubed plus 5 equals 1. Is there a solution to this? Now, there's a few ways you can go about this, but if you wanted to logically do it without a shadow of a doubt, if you wanted to deduce it in a logically sound way, what we can do is we can use the intermediate value theorem. So let's be very clear. One way to answer this is to use the intermediate value theorem, which I will denote the IVT. So here's what we want to do. If we want to use this, we need a couple things. We need to meet the hypothesis. So to do this, the first thing we need is a continuous function, f to be continuous, which it is, check. And then the next thing we need is we need a and b such that f of a is less than 1 is less than f of b, or, of course, f of b is less than 1 is less than f of a. We don't have that yet. So how can we reason what a and b to try? Well, a good thing is to try numbers that are simple to use and to plug in. So, for example, a good one to always try right away is 0. So note, for example, what happens if you plug in 0, or what happens if you plug in 1 or -1. There's lots of little tricks or little themes that you might pick up on to think about how you might go about doing this. So if we go back, what was the function? The function was 3x to the 15th, right? And so that x to the power 15 scares me because that's kind of hard to compute, right? But I start to also think about, okay, if I look at this guy, these odd powers make me think some things. They make me think that, okay, when input is negative, my output's going to be negative, and when input, or at least possibly negative, depending on what my value is, and then when my inputs are positive, I expect positive outputs. So what this leads me to try is the following. Now, you might not think of this the way I think of it, but here's how I'm going to encourage you. So my intuition suggests trying -1 to 0. So note, f of -1 becomes, well, if you plug it in, you get -3 minus 6 plus 5, which is, do the math, -4. And then f of 0 is easy. You just plug it in and you get 5. So this was a good first guess. I guessed right, at least. So clearly, 1 is less than 5, and it's less than -4. So what does the IVT tell me? Well, the IVT tells me the following. Well, let me be very clear, because how I shouldn't say the solution. So thus, a solution of f of x equals 1 is C, which is less than 0 and less than -1. So in order to use the intermediate value theorem, we need a continuous function, which I have because it's a polynomial. And then I have to figure out what interval I'm going to consider. And as long as my interval meets a certain criteria where L is between the two outputs, then I'm guaranteed to have a solution between my two inputs. Now, if you look at the homework, I was a little more, if you scroll down, I actually gave you the intervals to consider. So I gave you an interval. So for number 7, all you have to do is evaluate the function at -1 and 1, and then write and make sure that it meets the hypotheses. And then for number 8, you have to look at the interval 0 to pi/2. No, so Heather, that's a good question. You're not going to be able to find the actual solutions right now. Now, I shouldn't say that. If you look at a graph will approximate them for you. But the problem is, and here's sort of where you might think that I'm just blowing smoke up. You know, the problems 7 and 8 are simple enough equations that even though you can't necessarily solve them by hand, the computer's going to have no problem graphing them for you. There's not going to be any sort of, you can go to Desmos and graph them, and you can estimate the solution pretty easily just looking at the graph. But the point is, in more real sort of, in many problems, Desmos is not going to be of any use to you. The equations will be too difficult for you to just sketch on a graphing calculator or something, you know, of that magnitude, or not that magnitude, but something of that simple. And so, you know, in a real problem-solving sense, we're only asking you to verify simple ones like on 7 and 8. So the fact of the matter is, all we're asking you to show is that it exists. And so the purpose of this problem is to get you to understand how does a theorem operate? How do we use theorems? You know, in math, we call things theorems, but what is a theorem? How do we use it? Well, the theorem's job is to just guarantee in a logical way that the solution exists. You know, here's a good example that maybe this will help sort of. Well, first off, before I do this example, let me be clear. I don't want you to tell me the actual solutions. I just want you to show me that it exists. But a good way to think about it is consider this. Consider x squared minus 2 equals 0. You know, in algebra class, if I said, what's the solution here? What you might do is you might say x equals plus or minus the square root of 2. And that's fine. That's a symbolic answer. But if I said to you, what's the numerical value? So the problem here, this gives 0 insight on the value of the square root of 2. Now, you might say, well, that's not true. I could plug it into a calculator. Yeah, I get that. But what if, what the point is just doing symbolic algebra, it doesn't give you any particular insight on the value. And so at least using the IVT, so you can use the IVT to show, for example, that the square root of 2 is less than, say, 2, but greater than 3/2. Or excuse me, not 3/2. I'm losing my, writing things down wrong. Oh my God. Now you know. It's like, I think I may have had good old-fashioned stroke today. Anyhow. So you could actually show that using the intermediate, I keep losing my jaw, that, for example, the square root of 2 is less than 3/2. And again, I know you can go to a calculator and do this. That's not the point. The point is we want you to be able to reason logically. And then, of course, you can trap it in between here if you wanted. You can get a much better bound on it. And you can keep repeating the intermediate value theorem over and over again to get more and more values. So if you want a good feel for what I mean by that, you got to try this on your own. But to come full circle and answer your question, Heather, all I want you to do is write out, I want you to treat the problem just like I did back here. I need you to, this is the solution that I'm looking for 7 and 8, this sort of argument. Does the intermediate value theorem apply? Okay, great. Why does it apply? And then what can we conclude from it? Where is this solution located? Is it between 5 and 13? Is it between -1 and 1? And I'm actually I'm giving away sort of, if you look at the homework, I'm giving that away to you. So let me pull this up just to be very clear. I'm telling you, I'm giving away, you don't have to come up with the numbers to try. I'm telling you what to try. Yeah, so let's just do 8 since someone asked. Might as well. So let's do number 8. So we want to look at 3x cubed So here's the function we want. Now, this is not, there's a few ways you can go about this. We want to show that this guy has a solution. So what do I have to do? If I want to use the intermediate value theorem, I have to do the following. So to use the IVT, here's what I'll do. I can first rewrite the problem. So I'm going to rewrite it like this. And then I need a function, so I'm going to give f of x the expression that's on the left-hand side. So what I want to know now is if I want to use the IVT, I need to find two values that when I plug them in, I get something less than 0 and something greater than 0. So let's make some notes. So note f of x is continuous. And why is it continuous? It's continuous because it's the difference of a polynomial and the sine function. So trig functions are continuous on their domains, which means if I add or subtract two continuous functions, I get a continuous function. Okay, so the next thing I have to do is plug these values in. So note what is f of 0? Well, f of 0 is 0 plus 0 minus 1 minus the sine of 0, which simplifies to -1. And then f of pi over 2 is 3 times pi over 2 cubed plus 4 times pi over 2 minus 1 minus the sine of pi over 2. And now we have to kind of reason what the size of this number is. This is 3 pi cubed over 8 plus 2 pi minus 1, and then the sine of pi over 2 is 1, so this becomes -1. But I don't even care what this number is. This is clearly greater than 0. I mean, it's clear. I mean, 2 pi is bigger than 2, so this number, you don't have to think too much. Pi is 3.14. This number is clearly bigger than 0. Okay, so what do we see from this? Well, since 0 is less than f evaluated at pi over 2, but it's greater than f evaluated at 0, the IVT guarantees a solution C satisfying. C is between pi over 2 and 0. And so that is one way that you can write up solutions a correct way. There's other correct ways you could have done this problem. It's not the only way, it's just one. Does anybody have a question about this? Comment. No, you don't always have to, Heather, but in this particular one I did. So the question was, do you always have to rewrite it? No. I could have, if I go back to the original problem, I could have brought sine to one side and taken the number 1 to the other side. You always have to have a number on one side, whether it's 0. I always like to use 0 just because it's easier, but it works for any number. I mean, look at the other example we did. We used 1. So as long as you have a number on one side, this will work. Does that make sense? Going once, going twice. All right. Does anybody else have a question about this? So again, if you want to understand the intermediate value theorem, it takes some practice. It takes some, it's a different type of sort of thinking than maybe you're used to in a math class. Many of us are used to in math classes as just memorizing procedures and repeating them. The problem is that's not math. It's just not. I mean, that's sometimes what we do in math, but mathematics is different than just mimicking a procedure. It's about thinking. It's about logical deductions. And so this is a taste of that kind of thinking with the intermediate value theorem. Okay, so does anybody have a question, comments? Okay, so we're ready to introduce our next topic, and we'll do this briefly, and then we'll give you some examples, and then we'll go on our way. So so now that we've said a bunch about limits, what we can do is we can turn our attention to an extremely useful and important limit. So this limit is called the derivative. And its motivation comes from our discussion a few classes ago. And what was our discussion a few classes ago? We did some, we actually talked about it more than once. And that was, our discussion was about tangent lines and velocities. So again, let's sort of set the stage for how we motivated all this. So in our discussion of tangents, so in our discussion of tangents and velocity, what we discovered was the difference quotient. And it looks like this. So we spent some time talking about what this represented. how it represented the slope of a specific line. And then we even talked about it. We went to Desmos and talked about if we pick some A and fix it, and then we let H get small, what does this geometrically represent? And so what happens is it turns out this limit, if we take this guy, it turns out this guy is super useful. And since it's so useful, we give it a name. It's called the derivative of f at a. So it's so useful, it gets a name. So the derivative of f at a is denoted by f with this looks like an apostrophe. We call this a prime. And so how do we define this? F prime of a equals the limit as h goes to 0 of f evaluated at a plus h minus f of a all over h. I forgot the letter A here. So what we're saying is there's a specific type of limit. When we take the limit of a difference quotient, it turns out that this has lots of uses. And so since it's useful and arises in many different places, we give it a name. It's called the derivative. And so I just want to reiterate again that this reads right here. F prime of A. Or the derivative of F at A. So you can read it one of two ways. Of course, if my function was g, I would call it the derivative of g at a. Or if my function was m, it'd be the derivative of m. So if f prime of a exists for each a in some interval, we have a new function called the derivative of f. And it's denoted in an analogous way. So the subtlety here being, when we write a, we think of that as being some fixed number, but when we write x, we think in it as being some variable. All right, so does anybody have a question? So there's some other common notations you should be aware of that you'll see from time to time. Maybe you've already seen these before. Sometimes we might write df dx. We might write ddx like this. We might write dy dx. We might just write y prime. We might write capital D of f. There's lots of different notations. They all have their own place. They come from different historical perspectives. One of the things that you should understand is that calculus was sort of invented by two different humans around the same different time. And many of you know that Isaac Newton had something to do with this. But also there's another guy named Leibniz who was also one of the developers of calculus. And so they had their own notations, and then the people that learned from them developed their own notations. So there's lots of different notations. And so you kind of have to be sort of ready to see them all. And they also have different uses. Sometimes we might use one notation because it's easier to write than another one. Does anybody have a question? So another thing that is going to be of use to us that you will see. So we sometimes write a vertical bar with maybe x equals a. And this means to evaluate. So for example, I might write df dx with a vertical bar and then x equals a. What that means is that just means f prime evaluated at a. So again, it seems overwhelming right now, and don't get overwhelmed with notation. I'm not going to test you on notation. What I'm basically saying is be on the lookout for all these different notations. So what we're going to do is on the next homework, we're going to ask you to compute derivatives and develop formulas. And as some of you already know, the derivatives definition is a limit, but It turns out that there's going to be shortcuts for many of these things, but we're not there yet. Does anybody have a question? All right, well then I think we should end here. I'll post an assignment, and then I hope you guys work on them. And then on Tuesday, we'll go over all these examples. Any homework problems you want to do, I'd be happy to do them. So if there's some you still don't know how to do, don't be afraid to ask. If you don't want to ask through the chat, or you don't want to ask in class, send me an email and tell me which ones you want to go over. I'd be happy to do them. If you want to be anonymous, that's fine. And then we will prepare. I'll tell you everything you need to know for the exam on Thursday. Questions, comments? Going once, going twice. All right, then I will tell you guys to have a great weekend. And I thank you for joining in. And if you have any questions, please reach out, and I'll talk to you guys Tuesday. All right, thank you very much. Take care.